I should thank the organizers for inviting me, and this gave me an opportunity to meet a lot of old friends after almost 3 years. So, in a single slide, this is the summary. This is no equations, no plots, and this is an ideal talk for your post-lunch session. Okay, so you know what you should do. Fine. So this is something that you all know. This is what you already know about high energy physics. We have observed the Higgs and established the CERN paradigm. We have observed the neutron oscillation. And of course, we have indirect evidence of dark matter. And these are the things that we don't know about, the exact nature of the dark matter and all these neutrino puzzles, the origin of the baryon asymmetry, the naturalness problem, and things like gauge unification and quantization of gravity. So essentially, the next decade or the decade after that should be spent in finding answers to these questions. But this is I would say, India-specific talk. So it's just to tell you, particularly the younger generation, that we are not really upstarts. We have a long tradition for high energy experiments and theory. For example, I could start with D.M. Bose. He was a professor of Calcutta University. He built the first cloud chamber in India. That was in 1923. So we are almost 100 years from that. And then the famous cosmic ray experiments at Sandakphu by D.M. Bose and his student Raychaudhuri. They got some pion and muon tracks for the first time on emulsion plates. And of course, the famous Kolar Goldfield experiment by Srikantan, Menon, Narasimhan, and others. They observed the cosmic ray muons and got the first evidence of atmospheric neutrinos in 1965. Also did some proton lifetime studies and all that. And then, of course, our experimentalists performed and took part in L3, D0, and Bell, and not to say about lots and lots of theoretical studies. So, high energy physics, I would say, has 4 frontiers. I will talk only about, okay, you have already heard about these frontiers. I will talk mostly about the intensity frontier and the energy frontier. I will not talk about the theory frontier, because theory frontier, in a sense, is not a part of mega science unless you really need some computation intensive projects. But of course, this is an essential component of any experiment. And for the cosmic frontier, Pratik Majumdar will say a lot about this. So these are the main issues in various frontiers. For example, in energy frontiers, we have the Higgs properties to study more about the Higgs, the precision measurement and the stability of the vacuum. Then we have the new physics searches, essentially bump hunting, direct searches, also dark matter searches, and searches for long-lived particles. And then the development, the R&D for the future colliders and their precision measurements and all that. On the intensity frontier, we have flavor physics, neutrino physics. I will club neutrino also in the intensity frontier. And again, the precision measurement like dipole moments and atomic parity violation and all that. Then for cosmic frontier, again, okay, there's a part of neutrino physics also in cosmic frontier. Something that you already heard in the morning about the supernova neutrinos and high energy astrophysical neutrinos and all that. Then you have the dark matter searches. Again, this was covered in the morning in detail, and cosmic rays. So this is the bottom line, that all the frontiers need detector R&D and high performance computation. So these are the things that we should develop. So these are the experiments. As you all know, the Indian experimentalists are part of the CMS collaboration. In the intensity plus neutrino frontier, we have Bell 2 to be precise, INO and Nova and Minerva. In the cosmic frontier, we have Pico, about which Pratik will talk. And then we have the future efforts on in fact, it can be on so many things. It can be on colliders, on neutrino, on dark matter, on symmetry tests and all that. And also, please note that I will not give any details about the experiments. I am not qualified to do that. I will not name any individual people or institutes. And also what I call the future efforts, these are essentially based on the interest shown by the Indian scientists. Some have started, some are yet to start, and there might be new projects. There might be new proposals, which we'll see. Okay. So in the energy frontier, we have CMS. CMS India has 14 participating institutes and more than 100 scientists, and there are already more than 100 PhD from CMS India. And our experimentalist friends have delivered detector modules, electronic readout components for silicon-based pre-shot detectors, scintillator-based outer hadron calorimeter, silicon photomultiplier readout boards, and the RPC and UM detector modules. There have been lots of simulation studies and grid computing for tier 2 center is a TIFR, and there are lots of tier 3 centers. The major contribution is to the study of associated Higgs production and possibly charged Higgs production signals. We are also actively involved in the high luminosity LHC upgrade. And the important thing is that this should lead smoothly to future colliders like ILC or FCC. Then in the intensity frontier, we have Bell 2 at KEK. This, in a sense, is the ultimate precision flavor experiment with a projected luminosity of 50 attobarn inverse, and it will study in great detail the rare decays, CP violation, and also indirect search for beyond standard model. Bell 2 has delivered about half attobarn inverse so far, and as has been emphasized by our speakers, Diego particularly, that this is complementary to LHCb. There are 10 institutions involved with 42 people so far. Okay, I have taken this now. I should say that I have taken these numbers from our draft mega science proposal, and I hope that they are all correct. So this Bell 2 participation is again a smooth transition from Indian involvement in Bell, which was the predecessor of Bell 2. We have contributed in silicon vortex detector, detector calibration and computing, and 3 institutions are involved in Bell 2 grid computing. And the next aim is the development of a double-sided silicon strip detector for better resolution. This will continue till 2035. Okay. Then on the neutrino frontier, these experiments are situated abroad. This is our own experiment, the India-based Neutrino Observatory. This is essentially an atmospheric neutrino detection experiment with a 51 kiloton magnetized iron calorimeter. The detector elements are the resistive plate chambers. There are 30,000 RPCs. Okay, so the main task is to construct the underground lab as the detector, and there are more than 100 scientists involved from 20 institutions, or probably more. So what can INO do? This will probably determine the mass ordering, whether it's a normal ordering or an inverted for the neutrinos, and also determine the atmospheric neutrino mixing parameters. It can also probe non-standard neutrino interaction, CPT violation, even probably even Earth tomography. Another experiment on the neutrino frontier is NOVA and also Minerva. They are in Fermilab. This is initiated with the Indian institutes and Fermilab collaboration in neutrino physics. This program involves 9 institutes from India. And again, this is a smooth transition from earlier collaborations like MINOS. NOVA is essentially for precision oscillator to determine the oscillation parameters precisely. Minerva for neutrino nuclear scattering. And the Indian physicists have contributed in beam studies, detector operations, softwares, and data analysis. Also studies like final state PION or K production. Again, this will be needed for the future Dune experiment. Okay. For the cosmic frontier, this is a dark matter detection experiment, and as I said, this will be covered by Pratik. Now we come to the future efforts. So for any future efforts, we should have a roadmap ready for the next 15-20 years, right? And what we really need is more person power and sort of a mechanism of a smooth transition from the existing projects. Of course, it is high time to start the R&D unless it has already started. And this is true for both international and India-based projects. Now, these future efforts can be further subdivided into various categories like top priority projects, forthcoming projects, minor, and niche. And what I have not said is that high performance computing is an integral part of this. This will involve data handling and also for lattice studies, quantum computation, everything. So this is a list based on the interest shown by the Indian particle physicists. So there might be more projects added, some may be dropped. There might be some more modifications and all that. For the top priority projects, how much time do we have? Plenty. Okay. For the top priority projects, we have the collided things like ILC, CLIC, FCC or FCC PP, muon collider. We already have lots of work on ILC and muon collider, mostly theoretical studies and some simulation. Of course, we don't have a very big pool of experimentalists, so that is something that we should build up. And we will probably contribute in detector building. We already have expertise in plastic scintillators, silicon detectors, gas detectors, RPC, JM, and Cherenkov telescopes. And the next one is the electronics trigger and data acquisition. Okay, we also have experience on that. So they will be useful. Another top priority project is Dune, the deep underground neutrino experiment. Again, this is a natural continuation of NOVA and Minerva. This will test neutrino oscillation parameters, 3 neutrino paradigm, the mass ordering, and this may even probe the leptonic CP violation. So there are 2 detector complexes. One is a near detector complex in Fermilab, and there is another far detector in South Dakota. The Indians will probably contribute in the near detector. They have already started the construction of some straw tube tracking detectors, and also the development of RPC-based external muon detectors for the near side. And an agreement has already been signed between DAE and Department of Energy of US. So these are the top priority projects that we will have. There are some other projects, some other experiments for which Indian scientists are interested, and this should come up. One of them is participation in the detection for long-lived or very low-charge particle searches like Methuselah or Millikan, which is on top of CMS. Methuselah is based, okay, these are not too costly. This is essentially based on RPC and plastic scintillators, and we already have our experience. So with existing technology and a reasonable budget, we can participate in this. For neutrino, you have already heard about this, Hyper-K. This is a 260 kiloton water Cherenkov detector. The construction has already started, and some Indian institutes are already in. Okay, so we may contribute in detector construction and testing, also for developing software and data acquisition. The last one is the ultra high energy neutrinos, the IceCube Gen 2. This is still in the inception phase, so probably this will come up, say, in 10 years' time, roughly. We have interest in building prototype detectors and main detector components like scintillation and proportional counters, and of course in computation and data handling. For the minor projects, minor means you don't have to have a heavy budget for this. PICO is one for which Pratik will talk about, and there is Super CDMS. This is a direct dark matter detection experiment, which will probably detect, which will be able to detect dark matter of the order of GeV, and this is a region where the main challenge is to develop the highly sensitive detectors. Then there are some niche projects like the dark matter detection in the Jadugoda mine. This is a low mass dark matter detection experiments. This will either be in Jadugoda or maybe in the Ayanu cavern. Already some R&D are underway for detector fabrication, instrumentation, and calibration. And this will use superheated liquid detector with some chlorofluorocarbon target. Then there are other experiments like Teen. This is an experiment to observe neutrinoless double beta decay for Teen. This will probably be covered in the nuclear physics talk by Rudrajyoti. Then there is another experiment on sterile neutrino search. Some prototypes have been developed. Then we have this solar neutrino detection with deuterated liquid scintillator and observation of 7 beryllium lines with indium, electric dipole moment measurement, and all that. And the important thing is that there should also be feeder projects. I mean, this is where the younger people should come in. There should also be some feeder projects which will ultimately lead to these mega science projects. The last thing, of course, is the theory frontier. And there are so many things to talk about, so I will not spend more than one slide on this. We have the standard model calculations, beyond standard model, neutrinos, dark matter, and all that. On the standard model, we have a lot of works on higher order effects and flavor physics, lattice studies. For beyond standard model, all sorts of possible extension of a standard model that you can think about, or maybe even cannot think about. There are various genres like supersymmetry, extra dimension, composite models, effective theories, and for all of them, the collider studies and studies for low energy observables, indirect searches, development of effective theories, and all that. Okay, thank you. I don't need that. Then we have neutrinos, on which we have model building and simulation studies on dark matter, and also lots and lots of studies on the interface of astrocosmos and high energy physics like RD universe, inflationary models, and all that. And of course, then there are formal theory, including string, about which I really do not know anything. Okay. So that's the last one. The future is apparently looks bright. Apparently look because more because we have a huge person power pool. So we just need lots and lots of interested young people. We have to, and also we have to start at the earliest. That is, that is not always very easy, but yeah, we have to. Because once it starts, we will be late. We cannot afford to miss the bus. And again, we have to, we really cannot start. If we have a limited pool, we really cannot join all the experiments because we cannot spread our resources too thin. So maybe we have to prioritize. And the development of the pool is also a responsibility of the teaching institutes, the universities, IITs, ICERs. They must play a major role here. We need, and definitely need, this is where we are lacking really, a strong and active collaboration with industries. That's an absolute must. And also we have to nurture our strengths. We all know what our strengths are. We also know what our weaknesses are. So we have to overcome those weaknesses as well. Okay, so that's all.